Use a double integral to find the area of the region inside the cardioid, r is equal to 1 plus cos theta, and outside the circle, r is equal to 3 cosine theta. So the circle is graphed here in red and the cardioid in blue, and we're being asked to find the area of this region that is inside the cardioid and outside the circle. Now, since these two functions are symmetrical, what we can do is just find the area for one of the regions and then double it. So now we'll focus on finding this area. We're going to be using the area of a two-dimensional domain region formula, which is the double integral over that region, and our integrand is going to be 1 dA. And now we need to decide, are we going to be integrating with respect to r first or with respect to theta first? So let's zoom in on this region in order to determine what those limits of integration should be. If we integrate with respect to r first, we've got r going from 0 to the cardioid, 0 to the cardioid, 0 to the cardioid in this region, but then we're going to have a lower limit that's on the circle and an upper limit that's on the cardioid out here. Now, integrating with respect to theta seems like it could be a good idea because the limits are going to be the same on the top and the bottom throughout the region. But when we do that, the inside limits of integration cannot have thetas, so we need to solve for theta in terms of r in order to get those limits of integration. And when we solve this equation for theta, we get theta is equal to cos inverse of r over 3. And when we solve this equation for theta, we get theta is equal to cos inverse of r minus 1. And I'm not really feeling good about having those functions as my limits of integration. So let's go back to the region and think again about integrating with respect to r first. We have the same lower limit and upper limit throughout this region here, but when we get to this vertical line, that's where the limits start to change. So let's break this up into two regions, D1 and D2, and we'll say the area of this overall region is going to be the area of D1 plus the area of D2, and we'll start by looking at the area of D1. Now remember, we are going to integrate with respect to r first, and our inside r limits are going to go from 0 out to the cardioid, which is 1 plus cos theta. So let's pop these on as our inside limits. So down here we're looking at 1 times r d theta, and our inner limits for r go from 0 to 1 plus cos theta. Now let's think about what the theta limits are. On the cardioid, when theta is equal to 0, we get the r value positive 2 out here. And when theta is equal to pi over 2 on the cardioid, we get the r value 1. And then as theta continues to sweep in the positive direction, we'll see that when theta is equal to pi, that's when the r value is equal to 0. So our limits of integration for theta in this region D1, the theta values are going from pi over 2 back to pi to give us this region out here. So our lower limit is going to be pi over 2, and the upper limit is going to be pi. Now we're ready to integrate that first iteration, which is the integral from 0 to 1 plus cos theta of r dr. The integral of r is r squared over 2, and we need to evaluate from 0 to 1 plus cos theta. So we'll plug in the upper limit of 1 plus cos theta, and then subtract, plugging in the lower limit of 0, and then let's simplify to get 1/2 plus cos theta plus 1/2 cos squared theta, which now becomes the integrand on the second iteration. So the outside integral goes from pi over 2 to pi, and this is our new integrand. Let's recall that in order to integrate cos squared, we use the identity 1/2 times 1 plus cos 2 theta, and so this becomes 1/4 plus 1/4 cos 2 theta. And let's combine like terms one more time before we integrate. So now let's integrate to get 3/4 theta plus sine theta. And let's pull out that constant multiple and then integrate cos 2 theta to get 1/2 sine 2 theta. And then we apply the limits of integration. So we plug our upper limit of pi in for theta, and we also have, let's call this 1/8 sine 2 theta, plugging in pi. And then from that we subtract the antiderivative with pi over 2 plugged in. And now we evaluate and then simplify. And this is the area of that first domain region. We called it D1. So let's come back up here and begin to add these two things together. So our area of D1 was 3 pi over 8 minus 1. And now we need to determine the area of D2. Before we move on to that, though, I do want to make sure that we remember D1 is just this portion here, D2 is just this portion here. I think it'd be better to call the sum of these two something like the area of the upper domain region. Let's call the total area 2 times the area of that upper region, which is what we're working on now. So to continue working on this area, we're now going to need to find the area of D2, which is this region here. So let's zoom in and try to work on the limits for this second region when we're trying to find the area now of D2. We are going to integrate with respect to r first in order to avoid the inverse trig functions in the limits. But with integrating with respect to r, we see that our lower limit is the equation of the circle and the upper limit is the equation of the cardioid. So we're kind of envisioning this radial arm coming from the origin. We begin with the lower limit that is the circle, and continuing in this direction, we end up with an upper limit that is the cardioid. So as we build our double integral for the area of that second region, again, the integrand is just going to be 1, and we're looking at r dr d theta, which is our dA. The inside limits are the r limits, and as we just mentioned, the lower limit is the circle, 3 cos theta, and the upper limit is the cardioid, 1 plus cos theta. Now let's zoom back in to talk about the limits on theta. The theta limits are going to start with the terminal side that causes these two functions to intersect. So we need to figure out what this intersection point is that begins our D2 region. We already know what the terminal angle of theta is. We've already discussed the fact that that's theta is equal to pi over 2. So we need to figure out which angle theta begins this domain region. And that means we're looking for the intersection of these two graphs, or the theta value that causes them to be the same. So we set them equal to each other and solve for theta. So here we are, we're now going to solve for theta. Let's subtract cos theta from both sides to get 2 cos theta is equal to 1. Now we're looking for the angle whose cosine is 1/2. And in the first quadrant where our intersection point occurs, that's going to be pi over 3. So this angle is pi over 3, and our limits of integration are going to be from pi over 3 to pi over 2. So let's begin with this inside iteration. That is the integral from 3 cos theta to 1 plus cos theta of r dr. And again, we get r squared over 2 evaluated at these limits of integration. Let's pull out that 1/2 and then plug in our limits. So we plug in 1 plus cos theta and then subtract from that 3 cos theta. So let's do some arithmetic here in order to simplify this. Then let's combine like terms and distribute in the 1/2 to get something as simple as possible to use as the integrand for the second iteration. And so we have the integral from pi over 3 to pi over 2 of 1/2 plus cos theta minus 4. Let's go ahead and substitute in for cos squared, which is 1 plus cos 2 theta over 2, and we're integrating with respect to theta. Let's take one more simplify step before we integrate, canceling those 2's and distributing it in, and combining like terms one more time, and now I'm ready to integrate. So we get negative 3/2 theta plus sine theta minus the constant multiple of 2 pulled out, and we get 1/2 sine 2 theta as the integral of that last term, and we're going to evaluate all of this from pi over 3 to pi over 2. So now let's plug in our upper limit of pi over 2, and from that we'll subtract the lower limit plugged in, which is pi over 3. Let's get a unit circle up here to help us out. And now let's evaluate all of this and continue to reduce. And then we have 1 minus pi over 4 as the area of this second domain region. And we'll take that back up here and add it to the area of that first domain region. So the area of this upper section up here turns out to be pi over 8, and the total area would then be 2 times that amount, or pi over 4. Units squared, because we're talking about this total area in both of these regions.